So I want people to participate in the class actively, read assigned papers and chapters, and in some cases I will require you to submit reviews on the readings before the class. I'll set up, in fact, if you go back to the 571 page, last year we had a wiki set up where people will just enter their reviews of the papers they have read. Okay, mostly that's just to make sure that you're reading stuff. Okay, I don't quite know whether anybody else will read your review. I'm not particularly sure, but this will sort of put some discipline into actually making sure that you read the paper before you show up for the class. Okay. Okay, that's one part. The other part is learn, present the state of the art in some sub-area of AI. This is something that you're going to do. So the class would obviously look at some areas that I will pick, that I picked, and I'll actually talk to you about which areas I'm going to look at. But there are also, AI as a whole is much larger. In fact, there may be people here who wish that I was looking at a completely different set of chapters than the ones I'm going to be doing in this semester. And so in fact, what I would like for you to do is actually go to CCCI 2010, which I picked CCCI 2010 because that's the most recent general AI conference. Last time when I did 571, I picked ICCCI 2009 because that was the most recent general AI conference that was held then. Okay, I actually could not get you the online link yet, but I'll find some way of making the entire proceedings available online, at least within ASU, because I have the CD, I can just make it available. CCCI itself is supposed to make the entire proceedings available online, but they're very slow. But so you get to look at the areas in them and then think of some area that's of interest to you and read maybe 1 or 2 papers and present them. Okay. Now, I don't quite know exactly when you're going to present. Last year, we wound up doing the presentations. I mean, last year, not enough people dropped the course, so we had like 19 or 20 people left, and which meant everybody wants to give a presentation, which means I don't have time to talk about anything. And so we decided that, well, I thought people agreed with me in this common decision that we'll all meet an extra class, for some number of weeks in the end, and then that extra class on Fridays they would do it. We may or may not do it that way. It depends on how many people are there and how many different topics have to be presented and so on. So that's one thing that you would do, and then probably the most important thing is you will work on a semester-long project of your own choosing. Okay, you can actually I can give some topics for people that don't have any idea as to what could be a reasonable semester-long chapter term project, but you could also come up with ideas and then talk to me, and I can try to help you to see whether or not it is doable within a semester. Okay. Again, this stuff is highly unstructured. In fact, I think the most structured is this: do the midterm and the final exam. This is the one that wasn't there last time. I thought in a real graduate class, nobody really cares how you do in the exams. I know how to set exams. I know how to even get grade exams, but it wasn't very clear that in a graduate level class, that's the most important thing. But it was also the case that by the end of the semester, I had situations where some people really didn't do much of any of this, because there was nobody hitting you in the back saying, you have to get done, and so people thought they can do all of these in the last week and found they can't. And so I will have probably, I'll definitely have a midterm and might even have a final exam. That would be a structured one, but really the heart of the course would be, from your point of view, these 3. And this is the least structured, but that's what research is. I'm assuming, how many of you are PhD students here? Okay, so for those of you who are PhD students, this is basically what you're going to try and do on a larger scale. Try to find a topic that actually can be done before your family starts saying, how long are you going to be in grad school? Okay, and we're just going to do a miniature version of that, which is, just 1 semester long project. And so that's sort of a the part where you would almost have to talk to me so that I can give you an idea as to, using my superior assessment abilities, whether or not this is actually doable in a semester. Okay, and then if it is kind of doable and then you still decide not to do it, then the onus is on you. Okay, and this can be done in groups of 2. You don't have to do just a project by yourself. If there is another student in the class, we'll soon actually have, I guess, so Wednesday evening is the drop add deadline, I think. So as of Thursday, we'll know actually who is in the class, at least for 21 more days. And then so I'll give you the names of the people, for the rest of the class, and then you guys can, connect each other and see if you're interested in doing, joint projects. Okay, that's regarding grading. Any questions on this stuff? No? Okay. So what I'm going to do in today's class actually are 2 parts. In the next about 15 minutes or maybe 20 minutes, I will try to tell you what we did in 471, what topics I'm trying to do in 571, and then talk a little about, and then after that talk a little about some broad trends and swings in AI. That'll sort of set the stage for the course, and then I'll actually jump into the first topic, which is planning. Okay, which actually this is one class where you obviously wouldn't have read the chapter because I didn't tell you what I was going to do. But by next class you would read up what we're talking about. Okay, my hope is actually to do, try and go fast, but you can stop me. I know how to go slow. Okay, but I will actually, it'd be harder for me to go fast. But I'm assuming that you're all grad students, you're all very smart, and you also probably took 471. I don't want to bore you to death. Even if you didn't take it with me, you must have done some sort of an intro to AI somewhere. I don't want to bore you to death by repeating everything. But if things are getting hard, you stop me. You ask questions, and if you find yourself like completely cut off from the class discussion because you barely did any of these topics that I'm assuming you know, then we probably have to talk about what readings you have to do. Okay. Okay. So in 471, last time I did, this is approximately what I did. Now this is the week by week description. So we talked about intelligent agent design, which is essentially, what sorts of what kinds of properties of the environment make it harder versus easier to design, agents working in those environments. We looked at basically search. At that time, in fact, there used to be, we talked about it as a problem-solving agent, but in fact, in today's class, we talked a little bit about the fact that essentially problem-solving agents is a fancy name, is a different name for agents that are working on atomic representations of the world. Okay, that basically means, if those of you who remember, this is the stuff where we did A-star search, for example. I'm talking about the class I taught, but I'm sure you've done something similar. Okay, so if any of you have done Intro to AI and haven't done A-star search, please do tell me. That would be really nice to know, because obviously the orthodoxy is going out the window. But anyway, most people would have done A-star search, and that assumes essentially the normal assumption is that the states are black boxes. Okay, so the search algorithm itself just manipulates a queue, right? It manipulates a search queue, and it does not understand the internal structure of the nodes. If you remember A-star search, there is an open list, and it has, let's say, N1 and the node which is corresponding to, now each search node corresponds to some world state, okay, and some G-cast, H-cast, parent, children. These are the kinds of pointers it has. Now, if you look at this whole thing is really just algorithmic dependent, A star search dependent data structure. Okay, really the thing that is telling you anything about the problem you're solving is the state. But A star barely ever looks into the state. Okay, it only looks at the G value and the H value and it adds them up to decide what the F values are, and it picks the node with the lowest F value and expands it. Okay, that's the reason why we call it atomic representations. Okay, when you start having algorithms that take into account the structure of the state, okay, then you start having, that's where you basically start having non-trivial knowledge representation. So in 471, for example, we did, for atomic representations, we understood how to do A star search, blind search, as well as A star search. And we then, week 4 and 5, I mean, these two topics, there are topics on CSP. How many of you have done constraint satisfaction problems as? Okay. So that might be one topic that we will actually wind up assuming you know, but you may not know. So there are only 2 hands I've seen. So we may have to, you may have to go back and read the chapter at that, as and when things actually get required. In CSP problems, essentially, there is this idea that you have a state with state variables SV1 up to SVn, okay, and these state variables must take values. Okay, each state variable can take values from the domain of that state variable. Okay, now obviously the CSP problem is considered solved if you can provide an assignment to each of the variables. Okay, now if I just stop there, then obviously it's not a problem because any assignment would have worked. Okay, what makes your life hard is because there are constraints. The constraints say essentially what constraints can be thought of in terms of legal composite assignments. That means they'll tell you that first of all, the fact that each of these variables has a specific domain means already that this variable cannot take a value that's not in this domain. That's a constraint. You didn't think of it as a constraint, but it's a constraint. It's a one-array constraint. Okay, the second thing is I can also say that if SV1 is taking value V1, then SV2 cannot take value V3 and V4. That's a constraint between those variables. Or I can say if SV1 is taking value V1, the only legal things that SV4 can do is take value V7 and V9. Okay, a classic, there are many CSP problems that you can think of. 8 queens is a CSP problem. Putting 8 queens on a chessboard such that no pair of queens conflict is a CSP problem. Okay, so is graph coloring is a CSP problem. So is scheduling a CSP problem. If you have a bunch of jobs and a bunch of machines, and different machines have constraints, and different jobs have to be done in particular order, and you can write them as constraints. What's more interesting actually is the problem that you really all know as a computer science student. The satisfiability problem is a CSP problem. Okay, so satisfiability problem, you have all these variables are Boolean. Okay, and the constraints are what? In satisfiability problem, what are the constraints? By the way, I sort of jumped into the pool and started swimming, and I am looking once in a while to see how many of you are sinking, but I'm trying not to have a long, laborious introduction because this is a graduate level class, and hopefully, based on how lost you look, I might get an idea as to how many people have to be lifted out of the swimming pool by Wednesday. But we'll try this way. Okay, that's the only way I can figure out because there are variety of people with variety of backgrounds here. Okay, so in the case of SAT, the constraints are what? Propositional formula. So in fact, you can think of them as clauses. Basically, any propositional formula. Is a constraint. So if I say P and Q implies R, now all of a sudden I am saying while P can be true or false and Q can be true or false and R can be true or false, it looks as if they can do this independently, but there actually exist some constraints that they have to obey. They cannot take valuations such that, either, so if, for example, one valuation, if in fact a constraint I have is P and Q implies R, tell me a valuation that won't work, in the final assignment.
P and Q are both true, but R is not.
Exactly. Right? So that's a that's an assignment that you have to make sure. Whereas I also hope you remember that if either P and Q are false, then R can be anything, because logical implication, false implies anything. Okay? So you have, basically CSPs are really satisfiability problems. Okay? They have slight difference. In particular, you'll notice that you can think of satisfiability problem from a propositional logic point of view, and CSP can be thought of as variables which are basically multi-valued logical variables. They're not just true false, they are a bunch of values. Okay. Interestingly, actually, the theory for CSP and SAT, developed independently. There is enough commonality, but some people work on CSP, some work on SAT, and they talk to each other once in a while. But there are certain techniques and certain ideas that make a lot more sense for CSP than for SAT. Even though it is the case that given a CSP problem, you can compile it down to a SAT problem. Yes? Okay. Now, turns out that we also might need pest control here. I just saw like a bug. So if the rest of the class goes like a wave, that's because the bug is going that way. But anyway, when we talked about compiling CSP to SAT, that's actually an interesting point. I mean, one of the things I'm trying to do is first also tell you what I did, but also get you to think of some slightly important issues as with respect to the current AI status. Okay. If CSP can be compiled down to SAT, should there be really like an area called CSP and an area called SAT? Do you understand what I'm saying?
Depends on how efficient that version.
Okay, so this is actually a question that obviously it depends, right? I mean, and from a computer science perspective, if everything ultimately is a Turing machine, what are you guys wasting your time taking variety of different courses? Just build a high quality steam powered Turing machine and you're done, right? Okay. This issue of compilation and in particular RISC versus CISC. What am I talking about? RISC versus CISC. Instruction sets. Okay. Interestingly, similar kinds of trade-offs occurred in computer hardware design. You people probably weren't born, but at one point of time, Lisp was like the king of all the languages, or the queen of all the languages, and DARPA was pouring money to develop Lisp machines, which are highly micro-programmed architectures, which provide direct support to Lisp. Okay, so they actually do car and CUDA directly, for example. Many of the Lisp operations are done at the machine level. Okay, and then there is a company that, again, you guys, before most of you already forgotten, there's a company called Sun that came up and said, hey, let's do RISC. We just have a few instructions which makes it easier to keep improving the speed of the processor every year. Okay, even though today the Lisp machine is faster than the same Lisp being compiled on the Sun workstation of that year. 10 years later, nobody is working on these microprogrammed hardware because there's not enough of a market to support it. Okay, while you can actually compile the same Lisp program onto the RISC architecture and it actually runs very fast. Okay, so you can play this game both ways. You know, the argument that I just gave you is give up on CSP, just do SAT. But the argument that he was giving is sometimes by compiling, you might be losing structure. If in fact everything can be compiled down to Turing machines, then we should not really be thinking about problems in different. What is a security problem? What is a AI problem? What's a database problem? It's all Turing machines. Okay, this compilation issue comes up. In fact, you know, once I get to planning, we'll see that there is a representation called strips representation, which actually can be seen to be close to propositional logic. It's basically assumed state variables are Boolean. Okay, and whereas it turns out that many cases actually you are better off realizing that the state variables are multi-value. Okay, and so there are in fact planning technologies which are, many of them were based on the propositional ideas, and then they have been extended, and you know, we have seen variety of ideas that actually of improving that technology by just taking into account the multi-valuedness of the state variables. Okay, fine. So that's about SAT and CSP. Now, by the time we came to CSP, are we thinking of states as black boxes, or are we thinking of states as something with structure?
Structure.
They have structure. Okay? CSPs are a kind of search algorithms where in fact the states have structure. Okay? What's interesting is the notion of the goal for CSPs is not particularly interesting, because all you're saying is everybody should have a value such that no constraints are violated. Okay, and in particular what you do in CSP is you start with a state, quote unquote state of the world, where no state variable has any value yet, and then each action is to take a variable and give it a value, take a variable and give it a value. Okay, and so if you think from that point of view, when you come to planning, which we actually will do today, but I also did it that time, a little bit of it at least, is you can actually think of planning as taking the CSP representation, okay, except the actions are no longer just saying I'll basically pick a variable and give it a value. They actually check, I will only give a value, I will only be applicable to the state if certain variables have certain values, preconditions. If so, then I will doctor the state. I mean, doctoring of the state was being done here too, right? You started with like an empty assignment, and you kept doctoring it to have more and more variables having assignments. What's interesting in planning is you could actually say that the actions can say, I can only be applied if certain variables have certain values. And if so, then I will change these other variables to have these particular values. Okay, and that difference winds up becoming quite useful in expressing problems such as the agent is currently in a particular state of the world, and it needs to be in some other state where certain properties are satisfied. Okay, so planning winds up actually being the full generalization of atomic search to propositional level. Whereas CSP is a generalization of search, not fully, because the goals, you're not allowed to have arbitrary goals. You still, basically your goal has to be all variables must have values and no constraints are valid. Do you understand what I'm saying? So in A star search, if you remember, there used to be a thing called a children generator function, right? And then there is a goal test function. Okay, A star search used to assume these would be essentially opaque pieces of code that it has no understanding of. Okay, all the A star search needs to do is take a node, feed it to the children generator, it out comes a list of new nodes which are supposedly the children of the state by doing various actions. And then there is an opaque piece of code called goal test, and pretty much any piece of code would be a goal test. I could say, give me any state where the summation of the values of 4th and 7th variables divided by the value of the 9th variable is less than 4. That's a goal statement. A star search will get you there. Whereas CSP basically assumes that the goals are always the same. The goal essentially will always be just a sequence of, basically everybody has a value and none of the constraints are violated. Okay, so you could think of strips planning that we will look at a little bit later starting today, hopefully, as generalization of atomic search to propositional representations, with CSP being the middle point where the children generator is generalized, but the goal test is still essentially built in. There's only one type of goal test. Okay. Okay. And then what we did, so we did CSPs, we did SATs and all that fun stuff. And then we also, of course, when we were talking about search, we talked about local search versus systematic search. That was an important idea. The thing that I want you to remember about local search versus systematic search, a couple of things that I want you to remember is that, first of all, systematic search typically has to ensure that it will be able to exhaust the search space, and so it can then give you an answer saying no solution exists. Okay, if a search space, and you're asking the search algorithm to look for a state with a certain property, and unbeknownst to you there is no such state, then essentially a systematic search is the only thing you can use, because it can give you the guarantee of exhausting the space if in fact it's a finite space, okay, and then tell you no, there is no such state. Okay, to do that, systematic search winds up, basically in the beginning it has a lot of freedom, but then it needs to keep track of what parts of the space it had been, so that it cannot keep going in cycles saying, oh, I have looked at this node, or I didn't look at this node, let me keep coming back again. Okay, so systematic search, actually there are these two pieces that which is one of which is leave no stone unturned. This is, and then the other one is don't turn any stone more than once. Okay, this is kind of garbling the proverbs that you are aware of. I will leave no stone unturned in trying to find some particular person, let's say. Okay, so systematic search will make sure that every part of the space will be visited, and it also wants to make sure that no part of the space is visited infinitely often. Actually, what I wrote is don't do it more than once, but you already know systematic search procedures which do come back to the state more than once. Tell me one. Iterative deepening. Right? Iterative deepening search procedures, for example, do come back to some states more than once, but they only come back to them finite number of times. Okay? If you can come indefinitely often, infinite number of times, then all bets are off. Okay? That's systematic search. Now what happens, because they have to be systematic, because they need to ensure that everything, all parts of the space have been looked at, they need to keep track of where they have been. Okay? So they need to keep track of, has to keep track of where it has been. Okay? Every search strategy that is systematic has to somehow keep track of what parts of the space it has been, so that it doesn't come back to it, infinitely. What that means is, at some point of time, as crazy as it might sound, at some point of time, systematic search would be, remember that systematic searches that you all know is sort of tree searches, where you come down a branch and then you expand the nodes, okay? And then one of the cardinal rules in A star kinds of searches, or depth first kind of searches, is suppose you are here, okay, and there is some node which you can get here, which within the space, within the world, it's very close to you. But to actually get to that point using your search tree, you probably had to go somewhere here and then change the child and come down. You have to swing an entire branch to come here. Okay, Tarzan can do it. A star search cannot do it. Okay, and local search is a Tarzan. It can swing from any branch to any branch because it has no idea where it's been. It has no idea where it's been. So when you start from local search, you try to add things like taboo lists, saying at least some states, I'll keep track of about 15,000 states, okay? And if I ever come back to any of these 15,000 states, I don't expand them. But eventually, really, the only foolproof method of exhausting a space is keeping track of something like a search tree. Something like a search tree. Okay, now it actually turns out, although I don't know whether we'll do this or not, it turns out that theoretically, having a search tree is an overkill. Okay, there is a beautiful idea called dynamic backtracking, which probably I won't do much of in this class because it's beautiful in theory, but not in practice. It doesn't work that fast, okay? But if you have time and if you got interested in this discussion, go understand what dynamic backtracking does. Dynamic backtracking essentially does systematic search without a search tree. So it does not necessarily tie its hands down from the beginning. It keeps its freedom as long as possible. Eventually, all systematic searches, as they come down the tree, they lose freedom. Basically, when you are here, you can only look at this part of the space. Even if this guy is like enticing you, saying, I'm such a nice node, and you can look at me, right? You're right, I'm right next to you. But there's no way I can come here. I have to go all the way up here and come down here. In depth first search terminology, you need to do unbounded amount of backtracking and come down. And in doing backtracking and coming down, you lose a lot of work. So, because you have all these problems, there are ideas in systematic search such as DDB, dependency directed backtracking, and things like sticky values. What they try to do is, while you are going up and coming down, first of all, you go up to the level where you should go up to, to avoid the failure. And secondly, when you come down, you don't have to repeat all the search you did. Hopefully, you can use most of the working assignments still. Okay, so systematic search has both a plus point and a minus point. Plus point is in terms of the ability to exhaust the space. The minus point is in terms of loss of freedom. Local search, on the other hand, has a lot more freedom. Now, if you are interested in finding whether or not a problem has a solution, and you think that the problem has a large number of solutions to begin with, I just want to find one, okay? Local search is a great idea. Whereas if you actually think that the problem probably doesn't have a solution, and I want to prove that it doesn't have a solution, then local search is not good. Okay, you would almost think, why would anybody search to show to themselves that the problem is unsolvable, right? 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 Okay, so it turns out that the simplest way to do theorem proving, is what? Suppose I have a propositional knowledge base of a bunch of clauses, right? And I want to see, does this entail a clause C4? Right? That's actually I'm talking about now this. Right? That's not the representation. So if I give you a bunch of these guys, we looked at them as bad guys when we were looking at CSP because they are constraints. Constraints, you cannot say constraint and mean it in a good way. Right? It looks as if somebody's freedom is being curtailed. But I'll tell you a different way. Knowledge. That's a good thing. Right? So they're the same. Knowledge is constrained as seen as CSP side, or if you see it as, let's write down what kinds of solutions would be reasonable solutions for a problem, you write down these propositional logical statements, then suddenly you think of it as knowledge. Okay, now if I have a bunch of statements in my knowledge base, what does this normally mean? This essentially means I don't quite know the complete description of my world. Suppose, since I'm talking about propositional knowledge bases, suppose I have at the maximum of P1 to Pn are my propositions. P1 to Pn are my propositions. Okay, and this is a bunch of clauses made up of using only these propositions. May not have to use all of them, but some of them. Okay, if I did not give you this knowledge base, and I just gave you P1 to Pn as the propositions, and I say, I know that my world is made up of propositions P1 to Pn. I don't know anything more. Which particular world am I living in? It's one of 2 power n possible worlds. Do you understand what I'm saying? So, if there are n propositions and I don't quite know which world I'm living in, then I could be living in one of 2 power n worlds. Okay. Your friend, on the other hand, was, basically was told that they are living in this P1, P2, Pn where this true, false, true, true, false, true, blah, blah. So the specific assignment. Both of you are asked, in the world you are living, whether C4 is true. Both of you are asked that. Your friend is easy case because this is a single world. All you need to check is if this formula evaluates to true in this single world. If it evaluates to true in this single world, C4 is true for your friend. What about you? For you, if it evaluates to true in something up to 2 power n worlds, I mean if there are no constraints at all, there are 2 power n worlds, okay, then it would be true. In fact, there is really no formula other than true that evaluates to true in 2 power n worlds. Okay, now, what actually happens more interestingly is this is your friend and this is you. So you have the propositions and you have some constraints on the propositions. So the number of worlds that you are actually in is something less than 2 power n and maybe more than 1. Is it more than 1?
Not necessarily.
Not necessarily. Why not?
You could have a contradiction here.
Exactly. In fact, we could have statements here which are inconsistent with each other. And when you have knowledge base, normally, unless you are Sarah Palin, you assume that all the things you know must be true at the same time. You can't just say, I will talk this using this part of my brain, this using this part of my brain. They're both totally inconsistent, and still I'm happy. My brain doesn't explode. Okay? Logical brains will explode if you have inconsistencies. Okay, so if in fact there is the statement here which says P implies Q, and a statement which says P equal to true, and the statement which says Q equal to false, then this has 0 words. This has 0 words consistent with it. Okay, so in general for you, the problem of finding, for any agent, normally the issue is if they know something about the world, they'll try to figure out whether some new fact will be true there. Why would I care about that? For example, this agent might be having an action A1 which says if C4 is true in your state, then you can use me and I'll give you some effects. That's why the agent might be interested in figuring out whether or not C4 is true. Now, the simplest way for the brute force way for that agent to do it is enumerate all possible worlds that are consistent with its knowledge base and see if in every one of them C4 is true. If in every one of them C4 is true. If they are true in every one of them, then you can say yes, C4 is true. Okay, right? Now, obviously that's a dumb idea. You want to do this faster. How do you do it faster? It turns out this is a set of SAT formulae, right? What if I take C4 and add not C4 here? And check if this knowledge base corresponds to 0 number of words. Then that actually means that in the world that you live in, C4 is true. That's the only way. So for example, if Sarah Palin or somebody, I use some various names as the current examples. I used to use George Bush. He unfortunately retired, so I get to use Sarah Palin. But if you want me to use somebody else, send me a mail. We can try to use their name instead. So the question is, if you have a bunch of knowledge and then you are trying to prove, you're trying to say C4 is also true, to check whether or not you are consistent, I'll force you to take negation of C4 to your brain and see if it explodes. Logically, explosion means you're able to derive an empty class. If it does, then I actually proved C4. Now, what am I doing? I went off on a tangent, but I'll get back now. Okay? I was essentially trying to convince you that any knowledge-based agent writes the constraints about the world as a bunch of knowledge statements, and then it would try to use its existing knowledge to see if certain facts would be entailed. Okay, this is the entailment relation. And entailment computation is what an agent is always trying to do. Okay, now I proved to you that at least in the propositional case, the entailment is really nothing but taking the negation of what you're trying to prove, adding to the database, and then it becomes normal SAT problem and showing that this SAT problem has no solutions. That's where I got into this whole thing, right? I said, why would you ever think that a search algorithm would be tasked with a search problem saying, please show that there are no solutions? As long as we are at it, actually at one point of time, and this is of use to people in master's programs here. A couple of years back, at one point of time, there are two different master's programs here. One is MS, one is MCS, and they used to be in CS. I know there's one guy non-CS, but that's okay. And nobody outside of this room understands the difference, and most people here also don't understand. But it turns out that there are trapdoors. You get into one program, at least at one point of time, you couldn't come out of it. Okay. So one time I had this very strange experience. Two students knocked on my door and said, would you please sign this form saying you would not want to be our advisor? I have been asked by many people who knock on my door and say, would you please consider being our advisor? And I'll say no. And I was about to say no, and I say, hey, you asked a different question. You want me to say that I won't be your advisor. Why would you be interested in this? Well, it turns out that the advising office, apparently they had an MS advisor who has left the university and they now wanted to get out of MS and become an MCS student. And the advising office said, no, you can't do it that easily. Just because your advisor left the university doesn't mean that you're off the hook. You need to get 2 or 3 more people to disagree to be your advisor. Actually, they said, you should talk to at least 2 or 3 more people and see if any of them would be your advisor. And these students really didn't want to do a thesis anymore. So they had a search problem of proving that there are no advisors, right? So they were knocking on the various people's doors and saying, could you please say you won't be our advisor? Okay, so in general, even in real world, such as practical applications in computer science master's thesis, you would have search problems where the whole point is to prove that there is no solution. And in fact, a much more interesting technical point is entailment is computed by using SAT model checking. Except it wants to see that there are no models rather than see that there are models. Okay? Not surprisingly, since we are talking about that, remember the complexity of SAT problems? What's the complexity of SAT problems? That's the main problem from which all this nonsense about P and NP started, right? I mean, if Stephen Cook could just do something else, we wouldn't have been, stuck with this NP completeness business. He basically pointed out that the canonical NP complete problem is SAT. Okay, but SAT is about finding a solution. Theorem proving is showing that there is no solution. This entailment is also called theorem proving. Entailment is also called theorem proving. Okay? Theorem proving is showing that there is no solution, at least for propositional case. So what would be the complexity? So this is a conjugate problem of SAT problem. So what is the complexity of that? If SAT problem is NP complete, conjugate problems you put CO in front of it. Co-NP complete. Okay? And in fact, it's also known that in some sense, co-NP complete problems are harder than NP complete problems. In a weird sense, it's not a theoretical statement. It basically says that for some problem to be NP complete, all you need is that there is an instance of that problem that takes exponential time. Okay, so in fact there can be many instances that are extremely easy to solve. And many NP complete problems actually have the property that there are many easy instances. Okay, whereas co-NP complete problems, you don't have that much of a luck. Which also means that if you are trying to compile, remember the word compilation? Compile your favorite problem into an NP complete or a co-NP complete problem, you probably should compile it into NP complete, because at least if you are lucky, it will get solved faster. Okay, which also means that planning actually can be compiled down to SAT or theorem proving. The very first idea for planning was to compile it down to theorem proving, and that didn't scale well. Whereas compiling it down to SAT scaled well. Not as well as the current state of the art planners, but it does scale well. Okay, again an interesting, deeper point. Okay, so that's about propositional logic and knowledge representation, and the fact that sometimes, what you're trying to do is to show that there is no solution. Okay, then, so remember we had a bunch of words, and before you added not C4, I said one way of checking whether C4 is true is to enumerate all the words that are consistent with your knowledge base, right? And then see if C4 is true in them. Okay. You might be a statistician, and you might say everything can be done by sampling. So rather than enumerate all words here, I will sample words. Let's say, okay, I'll sample a word and see if C4 is true, and I'll sample one more word and see if C4 is true, and so on. Okay, now those kinds of ideas are in fact, even if you looked at enumeration of all the words, it turned out that you have a total of 10,000 words. In 9,999 of the words, C4 is true. In one word, it's false. What do you do? According to strict propositional logical view, essentially your theorem is not true. That doesn't mean that the negation of your theorem is true either. It just means that there is one word where C4 doesn't hold, in other 9,999 words C4 holds, so you still don't get to say you're done. Right? But it looks as if that's so much different, that's frustratingly different from a case where C4 is actually holding in one of the words and not holding in 9,999 of the words. And a logical representation doesn't differentiate between them. Right? So you want to talk about the number of models and the weight of the models in which the formula that you're trying to prove is actually true. That would be a nice way you go from logical knowledge representation to a propositional logical knowledge representations, to probabilistic propositional logical knowledge representations. Okay, now if you have done Bayes networks or Markov logic networks, any of you guys done graphical models as part of your intro to AI? Okay, so if we can get rid of him, I guess we can actually do intro to AI. None of you seem to have done anything. But I'm sorry, the graphical models are important. And we will probably do, I still would not want to just do the entire graphical models as part of this course, but since you're grad students and you have no more courses to do on the outside, then we can do it faster, hopefully. Okay, graphical models essentially are supporting propositional logical representations when you want to consider uncertainty. Okay, we did some, I normally do some on base nets in the Intro to AI class. It turns out there are, apart from base nets, there are Markov nets. There are two different graphical models with slightly different trade-offs, and we'll try to understand some of that hopefully here, but I don't do that in the Intro to AI. Okay. So this whole thing essentially was supporting, if you had supporting theorem proving and propositional inference here, this whole thing was supporting inference over uncertain propositional knowledge. So then what else is left in AI? We have deterministic knowledge, we have uncertain knowledge. What else is left? Non-deterministic. That's true. Non-deterministic essentially means that you don't even know. So in fact, that's a very useful point, but that's not what I had in mind right now, but since you brought it up, let's talk about that. Non-deterministic normally means you don't even know the probabilities over your worlds. And if in fact, it turns out that you're in a non-deterministic scenario, then it doesn't make sense to talk about the weight of evidence. Because unbeknownst to you, the models are such that in the 9,999 models where C4 is true, one model where it is not true, so you think, man, C4 must be true, but unbeknownst to you, the distribution over the worlds is such that 10,000th world has 0.999999 probability, and everything else is close to 0. So you're dead. In fact, the only world where it matters, it's like, many of the kids say, we really understand, it's just the test you gave me, I didn't seem to do well. Okay, the test that they give regularly on Mars, we do very well. Okay, but unfortunately, the weight for the test I give is very high. Okay, so in the case of non-deterministic worlds, all you can care about is weakly true, strongly true. Strongly true means it's true in all the models. Weakly true means it's true in some models. Okay, and sometimes actually, so in fact non-determinism means less knowledge. So determinism means full knowledge about where your world is. Uncertainty with distribution information means little less knowledge, but you still have the probabilities. Non-determinism means I have no idea. Okay, but there is another point I want to think about, which is we started at A-star search. And which was using atomic representations, right? And then we went from there to state variable representations. We went from atomic to propositional representations. And when we came to the propositional representations, we thought about how to represent and reason with propositional representations. Okay? In fact, when we talked about planning on the propositional case, most of the work wound up being done on the propositional case. We actually talked about that, and we'll do that here too. But one of the things that's left is if the states of the world are not black boxes, then from here to here you said they are no longer black boxes, but they are made up of state variables. And all your world knowledge is about assertions that are either true or false in the world. Okay, but what if your world has even more structure than that? Your world has relations and objects. Okay, so if you have relations and objects, basically objects and relations between them, then that's relational representations. Now you might say, oh, what's the big deal? Relational representations can be compiled down to propositional representations. But then I can say, well, that can also be compiled down to atomic, and that can be compiled down to Turing's steam-powered Turing machine. Okay. So the fact that it is compilable doesn't necessarily mean that it's the right thing to do. Okay. So one important issue is relational representations, and above the relational representations, you can have first-order representations, you can have second-order representations, and all that fun stuff. Okay, so at least in the Intro to AI, we did first-order logical representations and talking about how to write your knowledge in first-order logic, how to do theorem proving in first-order logic. Okay, and then we were strangely silent on first-order probabilistic representations. Not because I conveniently ran out of time, but because we don't have a good enough understanding yet of first-order probabilistic representations for Intro to AI. But for graduate class, anything that gets published is reasonable. Okay, so we do have lots and lots of papers on relational probabilistic representations. I think we have a better idea in the relational case. Okay, and what is more interesting is that we have to, there is also work coming out, a reasonable amount of work on first order probabilistic representations. Okay, so that's what we wound up doing there. And then we did some stuff on learning the knowledge, machine learning stuff. If you don't have much of this whole thing, looks at the enterprise of AI as an inference problem. People give you what you need to know. People tell you what you need to prove. And all you need to do is prove it. Okay, oftentimes you don't know enough about the world. You're given partial models, or you have to learn over a period of time by working in the world, by actually, living in the world and executing in the world. You learn more knowledge about the world. Okay, so the dream of AI, of course, is to do that learning. However, at the same time, there is no reason why, even if you are very much into evolution and Darwin and all that fun stuff, there is no reason why our machines have to evolve. They have us. We could tell them what we already knew. I know that might mean that they will become smarter than us faster, but that's an invariable thing that's going to happen. We'll always pull off the plug or something. But eventually, you want to have, you want to provide to the machines what evolution provided you freely. I mean, if those of you who think we learned everything we knew all by ourselves despite unnecessary interference from my parents and my teachers, I just learned it all by myself, you're deluding yourself, right? Because the brain that you came into this world with is a highly evolved organ with a huge amount of prior knowledge already built in. Okay, I mean, you guys know all this stuff, like a kid who is like an infant who is like hours old, when it is shown, when you go and, why doctors do this, don't ask me, but when you go and put a little rotten egg in front of this infant's, nose, apparently the infants cannot do this. And when you put a banana, most infants, except those banana haters, actually look happier. What the heck do they know about bananas? What do they know about eggs, rotten eggs? Well, we already, whatever the ancestors had, was essentially passed on by evolution. Okay, so our kids are coming into this world, I mean, including yourselves, coming into the world, supported by evolution. We don't need to wait for our machines also to take deep time to figure out how to become smart. We can provide a large amount of knowledge. But at the same time, eventually you do need to learn. That's what you had to do. Your parents told you some things, but you had to figure out some other things. Your evolution told you some things, your parents told you some things, and maybe a couple of teachers even told you some things, but the rest you had to figure it out yourself. Okay, so it's reasonable to think in terms of inference because there is a lot of cases where knowledge is available, but it's also important to talk about how to learn the knowledge, background knowledge. We did that too, a little bit of it in the intro to AI. Okay, that more or less is the view of intro to AI as I've done, and I also tried to use this to give you some of the salient ideas that I assume you would know, and these are kind of, there may be other things that will come out, but these are important. Okay, so if you look at Russell's book, right? The ones in green are basically the chapters we pretty much did in 471, so I would sort of assume you would know that. Okay, although I will make exceptions. If nobody knows graphical models and I go on and on talking about Markov networks and their relation to Bayes networks, it's not really going to be fun for me either. Okay, so we might do some of them. In particular, for example, we did Markov decision processes in the intro to AI, but we'll do them again here because I think very few intro to AI courses would have done them. And it turns out Markov decision processes are the A-star model. They are the atomic model atomic model where essentially you have uncertainty and you also have complex reward models. Okay, what we have seen in A star is you just need to get to some terminating state, that's called your goal state, you're done. Normally the life is, they keep saying this, right, that it's a journey, not the goal, especially when you get a bad grade in a course, we'll tell you, it's the journey, not the grade that matters. But really it is true. Okay, so the question of course is, how do you even have an understanding of what it means to do the right action when you still in an atomic model, but you have a complex reward model and you have uncertainty. And MDPs are essentially the way you start thinking about it. Now when I said that, that means with respect to MDPs, there will again be a propositional MDPs and a first order MDPs. They will be there too. Okay? But I would probably do MDPs. In fact, I will do MDPs again, and I'll probably do some more of the graphical models than you should have known, rather than just assume that you guys know already. Before I go forward, other things. The stuff in brown are things that I sort of touched on, but I didn't do too much of. The stuff in red, we didn't do at all in Intro to AI. This is what I have actually done in 571 in last semester. Okay. So basically we did beyond classical search, we had a whole bunch of planning under different kinds of conditions, different kinds of environments, deterministic. In fact, we assumed that you knew deterministic planning, and I went off to non-deterministic planning and stochastic planning. Okay. So what I plan to do this time is to start with classical planning, which will just take a class or two to kind of get you up to speed, and then we'll talk about non-deterministic and stochastic planning. Okay, and then we will go to MDPs, which I said I will talk about, which is basically atomic representations for more complex, reward models, and then talk about how some of the things in deterministic models can be used there. And we also did reinforcement learning, which I think I will do again this time. Reinforcement learning is a great case where the agent starts with partial knowledge about its world, and it executes in the world, and it is both trying to exploit what it knows and try to learn more than it knows. So that brings to open one of the fundamental trade-offs of an intelligent agent, which is exploration versus exploitation. Okay, should you keep taking more and more courses before you bite the bullet and start doing thesis? Because after all, more courses, you'll be even more wiser, and then you might actually find the real problem you'll work on. Or should you just say, hey, I've already completed middle school, let's start doing a dissertation. Okay, how far should I waste my time? Okay, it's something that we deal with all the time. Exploration versus exploitation. You do this in your dating, you do this in your courses, you do it in everything, and so reinforcement learning is a chock full of beautiful analogies to real life, but it's also an important problem. We'll talk about how to do reinforcement learning again, first at the atomic level, then propositional, and probably by the time we come to first order, we'll throw the hands out, because there's not that much work there. There are a couple of people, in fact, in the AAAI 2010, there are papers on first order reinforcement learning, but they are really at the research level, and it will be useful for you guys, but I may not be able to teach you that. Okay, so actually when I come back next class, I'll talk a little about the broad swings and trends and then go into planning, but you can look at this now and then we can have maybe 10 minutes of discussion and then go into planning. But I do want to show you this because this sort of brings together, the one underlying theme has been the representational hierarchy, like atomic, propositional, relational, first order. Okay, and this was actually more of a chronology of the semester in 471, and it's kind of, I drew this at that time, but it's also of interest to you because it's sometimes you would be making progress, sometimes you'll be making progress on this axis, and sometimes you'll be making progress on this axis. Okay, so for example, state space search is atomic. CSP is sort of propositional. As I told you, it's actually using structured state models, but doesn't have a complex reward. It basically has an inbuilt goal. Okay, propositional logic, of course, is at the propositional level. Bayes nets are also at the propositional level. By the way, I could have like a third axis, which is certainty, uncertainty. Okay, and then those will come on that, but I just took a projection on this. Okay, and then first order logic without functions is basically relational representations. And first order logic with functions, you don't expect to do compilation unless you have really large sheets of paper to write the propositional theories in. Okay, and then in the class itself, actually, that I taught, in the class I taught, basically I did first order logic and then came to planning, which is why, you know, this picture really is, okay, this picture, remember, this is the time with respect to Rao's Spring 2009 class, which is of course very important to the students who took the class that year and me, okay, but not necessarily that important for you. But you do realize that when you're looking at planning, strips planning got done at the propositional level. Why? Because at the atomic level, there is no difference between strips, there is no difference between planning and basically any A-star search, because it's just a path finding. Okay? And then MDPs, for example, were done at the atomic level, because when you are talking about non-determinism and complex reward models, it's not even obvious in what space are you finding a path. In particular, if your rewards are always on the final state, then you are still finding a path which ends in a particular state, except the space you would be searching in is not the space of states S, but the space of belief states, which is 2 power S. Which actually, you know, depending on what you want to say, you can actually say that if you have n state variables, right, you will have 2 power n states, and you will have 2 power n belief states. Okay? And if each belief state, and if you are talking about uncertainty, okay, then essentially you can have any arbitrary distribution over the belief states. I mean, a belief state is a distribution over the states. Okay, if you're non-deterministic, you're saying I'm in either state S1 or S7 or S8. Okay, and that's a subset of states, and there are 2 power n subsets. And since 2 power the number of states, which is the subsets. Since 2 power n is the number of states, the number of belief states is 2 power n. If you throw in the uncertainty, then what happens? Then what happens is you have this state which is S1, S7, S8. Your friend also has S1, S7, S8. You say this is 0.7, 0.2, 0.1. Your friend says 0.669, 0.201, 0.1. Different belief states. So in fact, once you have uncertainty, you are looking at an infinite space. It's a continuous valued space. Okay, now, which actually is an interesting point to talk about, which is we should talk about when we come back. All this while we talked about discrete variables. And even when I talked about systematic versus local search, we were looking at discrete variables. If you have continuous variables, would you even try doing systematic search? Unless you have really smart ideas and you can split the continuous variables into disjoint subsections, you will never be able to do systematic search. This is why calculus of variations is all local search. And this is why machine learning winds up using local search, because they are using parameters that are continuous valued. And so you do, local search is the only game in town, and sometimes those local searches can be shown to converge to the minimum. Okay, so anyway, so when we come to MDPs, we are actually talking about what to do at the atomic level when you have complex reward models and uncertainty. And and then we did at that time also multiple agents. And then by the time we went to machine learning, we were doing decision trees in that class. That was a propositional representation. In fact, none of you have done machine learning with opaque atomic representations. You all did it with propositional representations. And when we come to reinforcement learning, we'll actually do some atomic machine learning. Okay, so the point I want you to ask yourself after I leave here is, for everything you know, where is it?